Okay, so today I received one interesting question from one of our students. I think he is Ayush Anand Singh. So I thought that the doubt he had, it must have been, crept over some of the other students as well. So that's why I thought that it would be prudent on my part to, discuss that particular doubt. Okay, so his query was: suppose I consider the shaded region here, okay, which is nothing but the region bounded by the two semicircular arcs, the top circle is x squared plus y squared equal to 4, and the bottom circle is x squared plus y squared equal to 1. Okay, and then uh, he has worked it out. He said that the area of this region, say R, I mean area of R. So that turned out to be 3 pi by 2. And in my introduction today, I told you about change of variables where the original plan was the UV plan and the transform plan that was the XY plan. Okay, so here U and V, they are going to be replaced by R and theta. So I did something like this, if you recall. Like I had, okay, so if this is 0, this is 1, this is 2, and suppose this is pi, and then obviously, it is easy to find out that area of, say, suppose this is S, area of S, this is equal to simply pi, because this length is 1 and this height is your pi, so that makes the area pi. And the transformation under consideration, say suppose something like t, and you know that this transformation t is defined as your simply x equal to r cos theta and y equal to r sin theta. Okay, and his question was, why are the areas different? They are not coming as the same. So now I think I have got the doubt right. Is that you may be thinking that whenever we talk about performing integration over an arbitrary region in xy plan, okay, whatever area we consider in a previous plan like UV, they're going to be the same. It is not like that. Okay, please remember, it is not like that. You have to remember about that. And what I discussed in today's introduction, and as well as in my video lecture, is, let me again go back to this, and again I'll try to put you what exactly I was trying to do, because I was running out of time, so maybe it was not very clear to you. Now, if you recall in the lecture slides, lecture notes and lecture videos, we were talking about grid lines. Okay, see, instead of UV plan, I have considered this as R theta plan. Okay, so now and again we have told that the boundaries of one region considered in the original plan, that is going to transform into the boundaries of the transform plan over there. So now let us consider this one. Let us consider this one. If you look at this here, your R lies between 1 and 2, right? And your theta is simply 0 here. So if you look at the corresponding x and y coordinates here, so if theta is equal to 0, then you will see that x is simply equal to r and y is equal to 0. And what is the range of r? R goes from 1 to 2. So in the xy plan, so that means this boundary, if this is say S1, so it will correspond to this boundary. So this is say I call it say S1 bar. Okay. So similarly, if you now consider say this boundary, let me call it S2. So this is what here your x is sorry, not x, sorry, R. For S2, your R is equal to 2 and your theta varies from 0 to pi. Theta varies from 0 to pi. So that means this is simply going to be 2 cos theta and 2 sin theta. X equal to 2 cos theta, y equal to 2 sin theta. And as you vary theta from 0 to pi, it is going to generate this semicircular arc. this semicircular R. So this is the image of this S2. And again, interestingly, I see, look at this. This is S3. For S3, what was happening? Your obviously theta was equal to pi, and your R was from 2 to 1. You look at the direction there. R was from 2 to 1. So if theta is pi, then you can see that your x equals simply minus r, y equal to 0. Okay? Now you will see that when r varies from 2 to 1, so y will be equal to 0 and x will be varying from minus 2 to minus 1. So this is your image of this one, this boundary over there. So similarly, you'll be able to find out that the image of this is simply going to be this one, this one. Okay, fine. So now I think you are convinced that boundaries are going to correspond to boundaries in the transform plan as well. Okay, so then we were talking about some constant u and v lines here in this rectangle. Okay, so here, so basically we are going to talk about constant r and theta line. For example, say suppose say r equal to 1.5. So obviously, I mean, if r equal to 1.5 here, so then I am going to consider this straight line. I am going to consider this straight line. So then what is going to happen? It is going to generate a semicircle here because theta varies from 0 to pi, semicircle of your radius 1.5. So that means this will correspond to something like this. This will correspond to something like this. Okay. So similarly, what you will see that r equal to constant is going to generate curves like this. Is it okay? Fine. So similarly, when theta equal to constant, it is going to generate what? Suppose your theta equal to say what? So pi by 2. If theta is pi by 2, I am simply going to get x equal to 0 and y equal to r, right? So that is going to generate this line. Is it okay? Fine. So that means it is going to generate something like this. It is going to generate your something like this. Okay. This is what it is. Okay. So basically, what you have found out that like r equal to constant or and theta equal to constant, and for that matter, u equal to constant and v equal to constant, they are going to generate what? Some curves in the transform plan, right? So that means if I divide this region, for that matter this rectangle into sub-rectangle, if I consider a particular patch over here, so that is going to correspond to some patch over here. Is it okay? Fine. So that is why when we are performing integration in the xy plan, so then what is going to happen? I mean, if I consider this particular region having area say dA, so if there is a possibility that I can convert this integration over the curved rectangle, okay, as some integration over this sub-rectangular region, my job will be much easier. That is the point in set of variables. Okay, and that is where we were trying to find out that, I mean, if say the area of this region is say the A bar, right? what I did in today's class is that then dA, it is going to be equal to, in my class I was taking r as u, theta as v, sorry, it is going to be equal to this r theta, okay, and then dr d theta, okay. So that is what it is. And you should not think that whenever we consider change of transformation from some rectangular domain to some arbitrary domain here, their areas are going to be the same. It is not going to be like that. Okay, fine. And with that note, I would like to tell you something more here. So now let me concentrate on this patch and this patch. Okay. So now what I did, I considered. Now let me come to UV plan. Okay, I consider this is as U, this is as U plus delta U, and I consider this as, sorry, V naught, this as V naught plus delta V. And assume that this is a magnified version of this situation, and I was considering something like this. Okay, and what was the transformation? Transformation was something like RUV. So this is X UVI plus Y UVJ. Okay, and one thing you have to remember is that whenever I think about your U equal to constant and V equal to constant, then you will see that if say U equal to constant, then this is going to be a function of V on V, right? So that means I am able to parameterize this one, I am able to parameterize this vector in terms of a single parameter, this, okay? And that one is going to generate, some curve like this here in the xy plane, right? Similarly, if I keep your v constant, that means v equal to constant, lines here, they are again going to correspond to, in this particular case it is a straight line, they are going to correspond to some curves. Is it okay? Fine. So I have already done this part in class. Now what? So that is why I can always do, like say, I mean, if this is R U naught V naught, and then this one I have already told this is R U naught plus delta U V naught, something like that. Another thing I want to emphasize is that I told you that I am here. I am concerned about just the parallelogram coming out of joining this point to this point and this point to this point, right? And I was taking the area of the parallelogram to be the approximate area of this patch, Now, one thing I was telling you, just to differentiate between what we did in, your area of surface, which is nothing but the graph wave function of two variables, where we considered two tangent lines. I say that this is not, tangent line. This is simply two vector joining these two points. Of course, here the tangent also has a role, but that is kind of hidden. So what is happening here? Eventually, if you recall, I approximated this vector. If I call it A and I call it B, I approximated A to be equal to something like R prime U. Sorry, that RU, this is nothing but partial derivative with respect to U, and similarly B, this V delta V. Now remember this, okay, V equal to RV delta V. Now remember, although here A and B, this is approximate. Here A and B is not along the direction of the tangent, right? But their approximations are two vectors along the direction of the tangent. So basically what we have done, again, in fact, this parallelogram which is the sides, designated by this white color, okay, in fact, they are again approximated by a parallelogram whose sides are along the tangent to these two boundary curves at the point, at this point, u naught v naught. I hope that is fine with you all. Okay, and again, later on, what we did, I told you that eventually, this your dA, it was nothing but approximately your delta V. Now, if you look at this, this is going to be simply ijk, and this is going to be what? Here, I am simply going to get xu, yu, and here xv, yv 0 0. Because if you look at this, function, if you look at this, this function, then you will see that when I have kept v constant, r at say u naught v naught. If you recall that, when I kept v constant, then I will find out the partial derivative with respect to u, and when I keep u constant, then I would find out partial derivative with respect to v. Okay, and then this is, once you find partial derivative with respect to u, this is simply going to be xu at whatever point you take, and then this is going to be yu at whatever point you take. Okay, so that is why the components are this. So once you work it out, so this is, and remember there is an absolute value sign here. So this is eventually going to give you something like xu yv minus xv yu, this k, and then delta v, and this one we simply call as Jacobian of xy with respect to uv. Okay, del v. Fine. And so then what happens? This dA you simply replace by this, and what you do, if you take the Riemann sum, eventually they are going to become du dv. Okay, so that is the story behind all of this. Okay, I hope whatever I have explained, that is going to be helpful to you. So thank you.